Thank you. Good afternoon. I'd like to first thank the organisers for inviting me to be able to make a presentation at this meeting. I think it's a great honour, and it's also my first trip to Japan, so it's given me an experience of Japan for the first time, so I really appreciated that too. And I think Professor Gedanken has done all the speakers a great favour by so eloquently supporting your efforts and your activities. I'd like to echo that you are engaged in a next generation project, a next generation production of biofuels. And I'd also like to add that I think that we can think of energy production from these systems in different ways. We can think of them as producing liquid transport fuels for cars and jet planes. And we can also think of them as producing energy that is termed stationary energy. That is energy that's going to go towards processes such as wastewater treatment, where you replace the fossil fuel energy that you would be using to drive your processes with renewable energy derived from the algal biomass grown within your wastewater treatment plant. And I think also it's not just the energy production. You are actually have an opportunity to replace fossil fuels, and you also have then an opportunity to contribute to the reduction in greenhouse gas emissions. So you have the opportunity to generate energy and also reduce greenhouse gases. So I think you're on a really tremendously interesting path, and I commend you for it and for the approach you've taken. I thought I should just show you where I've come from. I'm in South Australia here, and Adelaide's here, and Melbourne's down here. And we are a state that is the driest state in the driest inhabited continent on Earth. So we also value water. So when you do wastewater treatment and you use algae for wastewater treatment, water is an important end product from your process. So don't just think about the biomass, think about the water that you've cleaned up and the water that you've produced and the water that can be reused. And that is a focus of the work that I'm undertaking in South Australia. And this is my city where I come from, Adelaide, and it has some tremendous beaches, and it's a very pleasant place to live, and it produces some really good red wine, which is actually irrigated by wastewater treated using algae. So when you drink red wine, you can think of algae at the same time. Okay, I'd just like to give you a roadmap. I'm going to talk a bit about the rationale for why we want to integrate wastewater treatment and algae, talk about something about algal ponds, and then take you through some of the research projects that I am involved in and that we're actively researching in South Australia, talk about the added value, and since I entitled this Opportunities, this is the opportunity part, and then I'm going to issue some challenges or where I think the bottlenecks in the technology are and where you might be well advised to have a look at improving. What's the rationale for integrating wastewater treatment and algal biomass for energy production? Well, I would draw attention to this report, which is relatively under-referenced, I believe, and it's from the National Academy of Sciences in the US. These were scientists who were not engaged in algal biomass production, and they were asked to review the sustainability of producing algal biofuels independently. And they noted, firstly, when we talk about using algae, the first issue about first-generation biofuels and perhaps second-generation biofuels was that they would use a lot of water. And that's true. They estimated the data was so poor, there was so little information of large-scale systems on which to get really good numbers, so the ranges of all these estimates are quite large, from 3 litres to 3,600 litres of gasoline. And the scenario they were looking at was the idea that this would be a 5% replacement of diesel biofuels, transportation fuels, 5% replacement with algal-derived fuels. So we were quite right to be worried about fresh water, but also they highlighted something that I think we quite often miss. That is that if you go to pure cultures of things like your Nanochloropsis and what I would call pet alga that a university or a researcher has, and they want to progress this particular algal strain, and they want to grow it in essentially a fertilizer mix of nitrogen and phosphorus. The estimate that this study provided was that if you went for a 5% replacement of transportation fuels by algal biofuel, you could be using up to between 44 and 107% of all nitrogen currently used in US agriculture. So there's a tremendous demand for nitrogen if you go to algae for biofuels. Equally, on the same scenario, you could be using between up to 20 to 50% of the phosphorus currently used in US agriculture. So whilst we talk about being worried about fresh water and we talk about agricultural land being in competition with agricultural land for growing algae or biomass crops for energy, I believe we're in danger if we don't really consider what we're doing, that we're going to be indirectly competing with agriculture for food because we'll be using fertilizers for food and we also want to use them for fuel. There will be a decision will have to be made about where that nitrogen and phosphorus is best used, and I suspect it will be food. So what did they recommend? Well, this is the good news, where you are already looking ahead and using wastewater, was they have to use, you should look at more detail about using wastewater for cultivating algae, or, and this is where there is some hope for the pure algal cultures, and certainly Ivani mentioned it in his introduction, was that we have to look at recycling nutrients from our first growth. We can't just have a one-pass system. We would have to grow the algae, harvest the algae, recover the nutrients, grow the second crop of algae on the same nutrients. You can't have a single pass. So, when you look at algae, you see that they need carbon, nitrogen, phosphorus to make the algal biomass. And when you look at some of these commodities, this is rock phosphate that has been mined. This is rock phosphate that's been produced. And this is a curve that's very like the peak oil curve. It's the concept that we may well run out of rock phosphate for agriculture, that we're on a curve and it will peak at about 2030 and will start to go down. That is open to contention because we're uncertain where the phosphate resources are, particularly in China, etc. And some people dispute this curve, but certainly we're on an upward trajectory. And if we believe the markets are always right, if we look at the cost of rock phosphate, it's been about $50 a ton US, but it has peaked to $400 a ton US. That's the phosphorus story. I think the phosphorus story is often considered. The nitrogen story is seldom considered. If we go to growing algae on defined media in large-scale cultures, we need a nitrogen source. And the current source of nitrogen is ammonia. And ammonia production is linked to liquefied natural gas because ammonia is produced by the Haber process. And it uses liquid natural gas as the hydrogen source to reduce atmospheric nitrogen to ammonia. So we're in danger. If we look at this is the Gulf ammonia price in the US, produced by the US Department of Agriculture, and we can see it tracks the price, and the price changes with natural gas. And again, at one point, it went up to almost $400 a ton for ammonia. And of course, you can see now that we're in danger of linking a biomass energy source to a fossil fuel source, because that's where we get our nitrogen from. And we have to rethink that, I think. We have to be very careful about how we move forward in that direction. It doesn't always work because the US now has started to use the novel sources of of petroleum products, the shale gases, the shale oils. And this has broken down a bit more recently from about 2010 because the US gas price has gone down and it doesn't quite track as well as it used to. So I hope I've convinced you that we need to be looking at wastewater, and that's exactly what your project in Project 2 is doing, is looking at wastewater for growing algae. Because the wastewater has a source of carbon, organic carbon that can be converted to inorganic carbon that the algae can use. It's got ammonia, nitrogen in the wastewater, and it's got phosphorus in the wastewater. So we have all the elements that we need to produce algal biomass. Carbon, nitrogen, and phosphorus is present in the wastewater. When we do wastewater treatment, we're focusing in this conference, this symposium, we're focusing on the production of the algae. But I'd like you to think about the added value that you get from growing algae in wastewater because you get wastewater treatment. So you have this biomass that's interesting to everybody in the room, but why do we use it in wastewater treatment? It's because the algae produce oxygen during photosynthesis. And as they produce oxygen, they are making that oxygen available to the bacteria, and the bacteria degrade the organic carbon by heterotrophic bacteria, so they treat the organic carbon, but most importantly, they release carbon dioxide, and the carbon dioxide goes back to the algae to enable photosynthesis. So you can see algae as mini oxygenators. They're biological oxygenators. You're not having to provide lots of energy to pump air into the wastewater. It's being produced by the algae. And as they take up these nutrients, the nitrogen, the phosphorus, and the carbon, the net result is you get clean wastewater coming out of the system, and you get your algal biomass that you're interested in. And we can demonstrate this. This is work we did in the 1990s, where we look at microalgae and their role in wastewater treatment. They can affect up to 90% nitrogen removal. We can show that nitrogen removal, this is the percentage nitrogen removal against a measure of the amount of algae in the system. And we can see we can get a linear relationship. The more algae we have, the more nitrogen we remove. We can show there's other processes involved with nitrogen removal. That is, at high pH, the ammonia leaves the system and volatilizes from the system. And we can also get phosphorus removal by uptake into the algal biomass and by precipitation in the wastewater. So what are we talking about when we talk about algal ponds? This is a picture from a group in Germany that I visited in the 1980s. And they had done a lot of the work that we now build on, that we're standing on the shoulders of, in the sense that they looked at various pond systems, round ponds. They abandoned circular ponds as being inefficient. They looked at inclined sloping planes of thin films. They abandoned that. And we've all settled, you've seen pictures already, we've all settled on these pond systems, high-rate algal ponds, which have circular channels and a paddle wheel that mixes the wastewater. These are pictures from Richmond in California, from Bill Oswald's group in Berkeley, and Hollister, which was a large system. So what we've settled on is we have the ponds that are shallow, up 30 to 60 centimeters. We mix at a very slow rate, which is surface velocity of 20 centimeters a second. That's just to keep the algal cells in suspension, to keep photosynthesis active and oxygen production for wastewater treatment active. We produce a reaction environment that is very homogeneous. It has high pHs in the afternoon, high dissolved oxygen contents in the afternoon, all factors that are good for wastewater treatment. And the big plus is that this happens because we have very efficient reaction environments. We have very short times to affect wastewater treatment. That means, importantly for South Australia, we don't lose as much water from evaporation because it's a shorter retention time, so the water is not left out evaporating for very long in your treatment plant. And we also have a smaller land area for treatment. So these are some of the systems that I've visited and some of the systems that I've built over my career. So this is a system in Scotland that I worked on for piggery wastewater. This is abattoir wastewater. And this is the system, this is another abattoir, this is another piggery wastewater in Northern Ireland, and this is the one I'm going to talk about next in South Australia. But you can see the designs are remarkably consistent in high-rate ponds. So I'm going to talk now about a process that is for rural communities and offers the opportunity for using algae to treat wastewater in rural communities. And I think as a next generation has the possibility of producing decentralized energy production from biomass in rural communities. That has to be looked at. So we have a scheme in South Australia, which I think is really quite innovative, but we don't brag about it enough. We don't go out there and tell everybody. So I'm producing it here for a bit of an advertising, I suppose. House in rural South Australia, it has to do its own wastewater treatment with on-site septic tanks. So in a septic tank, the wastewater comes from the toilet, the bathroom, the laundry, comes into the septic tank, the solids settle, and the oils and greases float, and you get a wastewater that is low in solids, low in oils and greases, and we take it to a pipe, and typically we use these things called waste stabilization ponds, and my abbreviation will be WSPs. So waste stabilization ponds, they are much deeper than the high rate pond. If you remember, the high rate pond was 30 to 60 centimeters. These are 1.2 meters deep. The wastewater stays in them for 36 days in this first pond, and then goes through a series of 4 other ponds, each one 7.5 days. So the wastewater, to be efficiently treated, stays here for 66 days, a very long retention time. This is a pond system. Some of you may know, if you like red wines, this is the Barossa Valley in South Australia. It produces Grange Hermitage, which is a very expensive wine. The wastewater is treated here, and the vines are here, and the wastewater goes for irrigation. What we were asked to do was, can we build a high-rate pond and demonstrate that a high-rate pond will replace these ponds? And you can see the large surface area here. So our project was to put a high-rate pond in, do the same house septic tank into the high-rate pond, and then reuse the water for good grape production. And of course, the wastewater is important in South Australia because Australian soils are very poor in organic carbon. So that when you add a wastewater that's got algal carbon in it, you're actually replacing organic carbon into the soils, and you get it as a soil amendment, and you get some benefit from that organic carbon. Just to show you, this was quite a challenging project because Flinders University is on the Gulf St Vincent. This is the Southern Ocean we're looking out at there, in here. And the small town of Kingston-on-Murray is about 250 kilometers away from the university. So it was a project, a research project done at distance, and we had to learn how to do that and do that cost effectively. The town we're talking about, Kingston-on-Murray, this is the River Murray. I think you've probably all heard of the famous Mighty Murray in Australia that runs for about 1,500 kilometers through the country and is a lifeline for many communities on its banks in terms of both drinking water and agricultural water. And our plant was, this is the site. You can see it's out in the bush, a remote site. This is a dirt road we travel up to go to our site. And this was the old system of the 5-cell waste stabilization pond that I described. And this is our new system with 2 high-rate algal ponds, courtesy of Google. The township is quite small. It has a population of between 150 and 300. It has people who are casual workers who come to harvest oranges and pick fruit. It's quite a good place to grow algae. It has very nice sunlight. It has generally nice temperatures, though it does go down to ground temperatures of about 4 degrees. The pond we constructed is about 200 square meters. We can operate it at a range of depths. We can change retention time, and it's mixed by a paddle wheel, and we have a weather station and a whole raft of monitoring equipment there. One of the things I'd like to point out is that when you do use algae for wastewater treatment, I'm not inoculating algae. I don't put an algal strain in. We just let the natural populations rip. We just let the natural populations turn up. They produce oxygen, they take up nitrogen, and the populations are organisms like chlorella, Cenodesmus, Ankistrodesmus, Pediastrum for the phycologists amongst you. They're what I would call the weed species. They're like the weeds that turn up in your garden. These weeds turn up in algal ponds, and they have really high growth rates. But of course, we've got an open pond system. So the biomass that we produce Carl Soder was a phycologist in Germany from about 1960s through to the early 2000s. He coined this phrase in 1980, albazod. It's a great name. You can go and baffle your friends by talking about albazod. But what it means is we have algae, we have bacteria, we have zooplankton. They may be eating the algae because the algae are the vegetables for the zooplankton. Apologies to the zooplanktologist. And we have also detritus, which is just the, if you like, the rubbish. The material, it's dead algal cells, it's cellulose, it's plant matter that's blown in. But it's a very different mixture from just talking about pure algae. It's a mixture that's in the system. This is a bit of a challenging diagram, but I'll take you through it. These are called beans. It's what's called a bean plot. And I'm keen to try and encourage people to do this because this shows all the data points that are within this collection of statistical analysis. These are all the data points that we have. And this is the spread of the data, if you like. And this is the mean of all the data that's in that bean. So this is the mean of those two populations. And this is the mean of all the beans. So all the data on this slide, that's the mean of all the data. And what you can do with this is you can see, if you look at your pond conditions, this is a cold pond. So what we've done is said, let's look at the data. 50% of the data on this figure was collected at pond temperatures below 17 degrees, and the other 50% was collected at pond temperatures above 15 degrees. And we've also varied the depth of pond operation. So we've got cold deep, cold medium, cold shallow. And then we could look at how the operating conditions changes the mean relative to the annual mean, if you like. And you can see that they don't behave very well. You don't get much algal productivity in a cold, deep pond. It increases when it gets less deep, and shallow, you get these two populations. And I think that's something, a challenge for these systems, is that we often get very wide variations in productivity within a particular season. And that's something we've got to understand better, is algal pond dynamics within the system. Why do we get these differences in populations, and why do they change so suddenly? And that's an active area of research. This is just to show you that in these systems with the short retention time, this is the water lost in the old system, the waste stabilization pond system with the 5 ponds that are 1.2 meters deep. You can see we're losing 2,000 liters. We're losing a lot of water. And rural communities, rural agricultural communities, are very attuned to water availability because they're agricultural communities. So they would like more water to be available for agriculture. This is the equivalent loss from our pond system that we've been operating in that area. So there's the difference between this and this is quite large. It means there's more water available for agricultural use, which is a huge environmental benefit in a country like Australia. And what have we achieved with this project? Well, we now can do a wastewater treatment step that previously took 66 days. We can do it between 4 and 8 days and get the same quality of wastewater. That's, I think, is a tremendous advantage. We can do it, and we use between 40 and 50% less surface area. That means this technology can be used in places where the previous technology was not appropriate because they didn't have enough land area available. It is easier to construct. It's only 30% of the earthworks moving the earth around to make your pond. There's less engineering activity to. We get productivities that are typical of these systems. They are typically, winter be about 5 grams per meter squared, up to 30 grams per meter squared. That's equivalent to 18 to about 110 tons per hectare per year. Now, I'd emphasize we don't harvest our algae. We use that as an additional carbon, nitrogen source for agricultural activity. We're not harvesting the algae. And the cost of construction is between 40 and 50% of the conventional system that was previously being used by these communities. And we've got more wastewater, and I'm really proud of the people who've worked with me on this project, because I believe now we're the first group anywhere in the world to have actually achieved regulatory approval for these systems. So we now have, our Department of Health has had the system independently validated, and we now have approval that this is an approved alternate system for rural communities in South Australia. So from my perspective, we finally moved from the high-rate algal pond for wastewater treatment, we've moved it from a research interest to implementation. And I think that's where we need to be with these wastewater treatment systems, is to get more of them on the ground, to get more people to understand how they work, and to have more algal biomass available for people who want to work on algal biomass utilization, that there will be now systems producing algal biomass to facilitate that research. This work in a small rural community in South Australia of 300 people led to Melbourne Water engaging us to do a research project with them. Melbourne Water treats the wastewater from the city of Melbourne, which is a population of about 4 to 5 million people. It has 2 wastewater treatment plants, and we're working on what's called the Western Treatment Plant, and it was funded by this group called Smart Water Fund. And the objectives were to design, operate, and evaluate the performance of a high-rate algal pond. Their interest was that they wanted, as your project, they wanted to look at using the nitrogen and the phosphorus in the wastewater to grow algal biomass, to take the algal biomass out of the water, and to turn it into energy. So they wanted it as an energy source to begin with, energy from wastewater. And they also then wanted to look at wastewater treatment using the system and to get some experience about how these systems work. We then wanted to evaluate the pond design and climatic impacts, as you'd expect. How does it vary with climate? And importantly, with moving to these bigger systems, we're now able to provide more real-world data for life cycle assessments. So we've got these systems to a point now where we can get real data off systems that are 200 square meters treating wastewater, etc. That's a big advantage too. Excuse me. So what do we have at Melbourne Water? Well, firstly, the wastewater comes in down this transfer channel here, and it goes to, these are covered anaerobic lagoons. So the wastewater goes in, the covered anaerobic lagoons. That means it produces methane gas as an energy source, biogas. That biogas, the methane, goes to an on-site power station. So Melbourne Water were a great match to the technology, because they are already generating methane from the incoming wastewater. It's going to a power station. This is the on-site power station. That has a power rating of 10 megawatt hours for electricity to that wastewater treatment plant. So that wastewater treatment plant is already 90% self-sufficient in energy from the biomass, from the biogas produced from the wastewater. One other thing I'll just explain is this lagoon water here, this is wastewater here, so the wastewater comes in here, goes through an aerated lagoon to oxidize ammonia, and then comes into this lagoon. And the wastewater from this lagoon is taken to the power station, and it goes through here, these tanks, to remove hydrogen sulfide. Hydrogen sulfide, when it gets combusted in a generator, turns to sulfurous acid and sulfuric acid, and it causes corrosion of the parts of the generator set. So they have to remove the hydrogen sulfide. And using the wastewater, they strip the hydrogen sulfide out in these counter-current stripping systems. When they strip the hydrogen sulfide out, they also strip the carbon dioxide out. So we had an opportunity here to look at how wastewater on its own and wastewater enriched with carbon dioxide, how did that affect algal growth and wastewater treatment. So it's a really nice... this is the construction phase. I think this is always interesting to see that you tend to see the the final phase, but there's a lot of work goes into building these systems with shaping the ponds, putting a sand base down, putting some geotextile liner on, a microbiologist pretending to be an engineer, then the lining, a plastic liner, we have to line our ponds to meet EPA regulations, and then the final handover on, this is in a July Melbourne day, and you can see it's not particularly, the image you have of Australia has always been blue skies and sunshine, isn't always the case. So what did we do? Well, what was the outcome of the construction phase? Because I think if we're now moving to application of the technology, we need to understand the problems of developing that technology and putting that technology on the ground. Well, I like to think, and we've been complimented, that the Flinders University design works well. It was robust and there were no teething problems, and we've done it. This is about the 5th pond system I've built, so I'd like to think I know what I'm doing, you know. What are the challenges? Well, excavation. This part here was very time-consuming to actually do this using earth banking. Small ponds are expensive. That's one of the areas we haven't really got very good cost estimates for larger systems because we haven't built very many large systems. And we're going to start a design study next year to try and get some better figures, hard-nosed figures, hard-nosed civil engineering values for construction of these systems and how we go about doing it. What's the research aims? Well, we want to know about how much algae we produce. We want to know about the algal species. We want to know what the algae contain. That's all part of the project. And we want to look at the wastewater treatment in terms of organic carbon treatment and nutrient removal. But we also, because we're going to reuse that wastewater has to be safe to people who come into contact with it. So that's another issue when we start talking about algae for wastewater treatment. We need to know how the pond system works to remove pathogenic organisms like salmonella, like adenovirus, hepatitis. We need to know that these systems have some measure of disinfection potential. And then we did 3 studies, which I'll go through very quickly. We looked at this addition of CO2 to wastewater. We looked at how depth and retention time affects the performance. And we produced a data set over a year of treatment performance and algal production. I won't go through this, but we're using autosamplers to collect the samples. We do the analysis at Flinders. We do that at Flinders. We have continuous online monitoring for DO, pH, and temperature of the pond systems here. And we use weather data from the Bureau of Meteorology. So the effect of CO2. So again, this is the power station. The wastewater goes through. It goes through these columns. The CO2 and the hydrogen sulfides removed, and we could put wastewater into this pond. Was the wastewater with CO2, and in this pond we just put wastewater without CO2 addition, and we compared the performance of the system. I'm not going to show you any data, but what the results? Yes, we got a 40-fold increase in carbon dioxide in the wastewater after it had been scrubbed from the biogas. And I emphasize it's the biogas before combustion. It's the biogas entering the plant before combustion that we've taken the carbon dioxide out of. But what we found was that CO2 did not increase the algal biomass production. And that's because, if you remember at the start of my talk, we already have a very large organic matter pool in wastewater. The bacteria break that organic matter down to carbon dioxide, and the carbon dioxide goes into the algae. So if you've got a large organic carbon pool, the addition of carbon dioxide doesn't necessarily lead to an increase in algal production. That's one, I think, important message. There is a confounding factor. We might have some influence of the hydrogen sulfide that was stripped going into the waste ponds, and we got the normal set of organisms we'd expect: chlorella, Cenodesmus, etc. Wastewater was what we'd expect. There was no real benefit from adding carbon dioxide. We got the usual percentage removals, the usual efficiency in terms of wastewater treatment. And I think that's an important part of this study, realizing that CO2 doesn't necessarily. With having 2 ponds, we can do the taking the same wastewater and put it into what we call the north pond and the south pond, changing hydraulic retention time, changing depth, and then looking at the performance of the system, which is again is an important outcome. And here, just to show you, particulate organic carbon is a measure of the amount of algae you've got in the system. This is the amount of organic carbon, this is the retention time, and this is the sample location. So this is the water coming into the plant. This is the water after it's been treated, as it were. This is the organic carbon coming in. This is the algae going out. The blue is 30 centimeters depth. The green is 40 centimeters depth. And you can see as we increase the amount of time the wastewater stays in the pond, the amount of algae increases over with retention time. With the 40 centimeter pond, we get an increase from 2 days to 4 days. And then it doesn't quite step up because this is when the onset of winter and the light and the temperature changes. And that's a challenge to all this research when you have seasonal changes in light and temperature. Effect again, well, algal productivity increases with increased retention time. Nitrogen removal was similar to what we've had in other systems. It was good at disinfecting the wastewater. And what we'd all expect is that the pond activity was seasonally affected. There was lower production in winter than summer, but the dry matter productivities were in that realm again of between 3 to 24 grams per meter squared per day. And these are pretty good productivities for dry matter production. And I'm just going to quickly do this one, the longitudinal data set. This is the months of the year. This is the dry matter content, the amount of biomass you have in the system. And you can see you get a seasonal change. This is spring coming to summer. Sorry, this is winter coming to spring, summer, and then autumn. You get a change. And again, in this Melbourne system, we also had these periods of short-term high productivities. And we see that, I've seen that in pretty near every pond system we've operated. And it's really something that we need to pay more attention to. Take-home messages. Our design worked well. We've got a construction system study going on in 2016. In this system, with this particular organic carbon content, there was no advantage to adding carbon dioxide. And I think that's important from a cost point of view as well. One estimate from colleagues in New Zealand is the cost of building a CO2 addition system might be 30% of the cost of building the whole system. It's a significant capital cost. So we really have to know, do we need to add CO2 to wastewater? And this study suggests that this organic carbon content, we probably don't. Shallow ponds perform best, though you could consider changing that configuration where you've got a surface area problem and you want to minimize the surface area for your pond operation, and we get seasonal variation. Okay. The previous speaker has already considered this, that why are we interested in algae? Because they're good, they produce large tonnages compared to traditional agriculture, so we should consider them if we're interested in biomass energy production. And we've already reviewed this. You could take the low benefits of fertilizer, soil conditioner, composting. You could consider, on another project, it was put to us that we should grow algae to feed pigs and replace soybean and barley that's currently fed to pigs. Why not feed algae? You could grow fish. You can use it for chemical feedstocks. Moina is a product in Japan that's been produced from Botryococcus as a cosmetic. And then we can go to the energy side. And this is work that I did when I first started in this area in the 1980s, would you believe? And you can produce energy budgets of the amount of sun, the amount of algae you can grow, how you can harvest it cheaply through sedimentation, how you can move it through an anaerobic digester, how you can make electricity. And then in this study that we did in Northern Ireland, we had a 0.3% solar conversion to energy in that system. So the technology and the view, the opportunity, if you like, considering the title of my talk, the opportunity is to harvest the sunlight through algae and produce energy. That's the opportunity. The other benefit, of course, is that algal biomass comprises of 45 to 50% carbon. The estimates everybody I think has settled on now on about 1.8 tons of carbon dioxide taken up for every ton of algae produced. And you can get between 30 and 40% of algal carbon converted to methane to produce energy. And if you burn that methane rather than a fossil fuel, then you get another half ton of CO2 abatement. So you can have a CO2 abatement system as well by growing algae. But I'd also commend to you what I stated at the beginning, was that if you grow algae, you are also using much less energy. So these are conventional activated sludge plants, extended aeration for nutrient removal. And the energy estimates in terms of kilowatt hours per megalitre treated range from 40 to 230. Ours are 60 to 110 from work we did and other people have done. So there's a considerable energy saving. So if you use algae to treat wastewater, and you're not using a lot of energy, you're not using a lot of fossil fuel, and you also save on greenhouse gas emissions. So there's another strategy, another benefit there. What are the challenges? I don't think we've learned from history. And I think we should always encourage our PhD students to go back and look at the old literature. I'm old. I've had this 30 years in this business, and I keep telling my PhD students, don't just think because you can electronically search it and all the data's there for 2000, you've got to go back further. We can go back, this period here after the Second World War, there were already work going on in Germany. Glycerol production for explosives was actually conducted using diatoms at the end of the Second World War. They were already growing algae to produce glycerol. The Burley Report, 1953, they highlighted all the problems we still have with algal biotechnology. We have the blip in the 1970s, a lot of work done there again for liquid transport fuels, and then we have this blip in energy and greenhouse gas abatement. And the challenge is, I think, that we need to spend much more effort on, and I think we might have not done that in this iteration of interest in algal biotechnology. Biosolids recovery. We have to get not only a net return on dollars invested, we also have to get a net return on the energy we put into the systems in terms of culture and harvesting and extraction and esterification. That needs to be really carefully looked at. And we can get the energy recovery from transport fuels, diesel, biocrude, but also I think we should be thinking more about stationary energy, anaerobic digestion, combined heat and power systems. And the problem is, we all know algae are small, you can't filter them, the microalgae you can't put through a strainer efficiently. They have a density similar to water. Water has a density obviously of 1, so these things don't settle very well, they don't float very well. And the methods we've got are centrifugation, energy intensive. We can flocculate and get them to sediment. We can dissolve air flotate. We can try and filter them. We can get sedimentation. We can use other biological species like fish and shellfish and zooplankton to harvest the algae because they're bigger to take out of the water. We can get zooplankton out of the water more easily than microalgae. And these are some of the systems that have been used. This is a system that was in Florida in the 1980s where you get the algae to concentrate at the center and then dry them on tables. You can go to the expensive systems of microscreeners and centrifuges to harvest. They are hungry for energy, so they do a lot of damage to your energy budget. Dissolved air flotation, where you blow air into the water and the algae float and then they're skimmed off. And then you can put them through a V-belt press and they actually will go as stackable. They'll be so dry they can be stackable solids in a container. This is in California, very expensive dissolved air flotation. You can see the engineering that goes into that and the amount of energy that might be thrown at that. This is a system in South Australia, removing algae so we can reuse the wastewater for agriculture. This is a $23 million plant to treat 150 megalitres of water a day to take algae out of. So the conclusion is, I think the opportunities remain as they were in the 1950s. They are tremendous organisms, high growth rates, tremendous potential for food, fuel, and fertilizer. I think the early win, in my view, the early win is wastewater treatment. is taking the benefit of energy-efficient wastewater treatment, and the challenges, I think, remain as they have done from history, that we need to have cost-efficient solids separation, energy-efficient conversion technologies, and in the wastewater area, I think the water utilities already do anaerobic digestion to produce this stationary energy, and I think that's where the early win is for this technology in my view. I'd like to just thank the people who've supported this work from Melbourne Water and Smart Water and Flinders. And I'd like to pay tribute to this man, Neil Buchanan. He was my postdoc. He was a sterling, excellent researcher, excellent supporter of PhD students. And sadly, he passed away all too early in the 2nd of July this year. And he's been a great loss to applied phycology. Thank you very much.